Hello everyone, and welcome to today's presentation on mechanical systems in wastewater treatment. I'm excited to have you here as we explore the vital role that pumps play in our wastewater collection and treatment processes. On this first slide, you'll see the title of our talk, along with a brief overview of what we'll cover. We'll discuss different types of pumps, their classifications based on the materials they handle, and the conditions under which they operate. Most importantly, we'll highlight how essential proper operation and maintenance are for ensuring our systems run smoothly. So, let's get started and dive into the fascinating world of wastewater pump systems. Now, let's take a look at the two main categories of pumps we typically encounter. First, we have centrifugal pumps. These are designed for high-flow, low-pressure applications. You'll often see them used as booster pumps or primary service pumps because they can move large volumes of water efficiently. When dealing with water, these pumps usually operate at a head of around 200 to 300 feet, but for wastewater, the head can be as little as 50 feet. An important point to remember is that flow rate in centrifugal pumps tends to change when pressure changes, making them suitable for applications where flow variation is acceptable. On the other hand, we have positive displacement pumps. These are quite different because they are used for low flow, but high-pressure scenarios. Think of high-pressure water jet systems or sludge and chemical feed pumps. They can generate pressures exceeding 2,500 feet of head, which is substantial. Typically, their flow rates don't vary much when pressure changes, which makes them ideal for precise dosing or high-pressure applications where consistent flow is critical. Understanding these differences helps us select the right pump for the right job, ensuring efficiency and reliability in our systems. Let's take a closer look at the key operational differences between centrifugal and positive displacement pumps. First, with centrifugal response, when the discharge pressure increases, you'll see the flow actually decrease. Conversely, if the pressure drops, the flow tends to increase. This means that the output of a centrifugal pump varies depending on the system conditions, making it more adaptable but also more sensitive to changes in pressure. Now, moving on to positive displacement response, this is quite different. The flow remains constant regardless of changes in discharge pressure. No matter how much pressure fluctuates, each pump stroke consistently delivers the same amount of fluid. This consistency is particularly critical when you're dealing with applications like precise chemical dosing or sludge tracking, where accuracy and reliability are essential. Understanding these differences helps us choose the right type of pump for specific operational needs, aligning with our overall goal of optimizing efficiency and accuracy in our systems. Let's take a closer look at how centrifugal pumps actually work. Think of a centrifugal pump as a device that moves water by using centrifugal force. Imagine swinging a bucket of water in a circle. The water stays in the bucket even when it's upside down because of this force. If you made a hole in the bottom of that bucket, the water would be pushed out through the hole due to the same centrifugal force. Now, inside the pump, there's a key component called an impeller. The impeller is like the heart of the system. It spins rapidly. Water enters the pump through the center of the impeller, which is called the suction eye. As the impeller spins, its vanes, like blades, grab the water and sling it outward into the pump body under pressure. This pressure from the vanes is what moves the water out of the pump and into the rest of the system. At the same time, the spinning action creates a suction that pulls more water into the impeller, keeping the flow steady. So, in essence, the impeller's rotation creates the centrifugal force needed to move water efficiently through the system, making centrifugal pumps a reliable choice for many applications. Let's take a closer look at impeller design principles. First, when we add more vanes or increase their sweep, we see an increase in discharge pressure, which means the pump can push water more forcefully. However, this comes with a trade-off. The flow rate, or how much water moves through, tends to decrease. Conversely, if we reduce the number of vanes or their sweep, we get the opposite effect: higher flow rates but lower pressure. Now, especially in wastewater pumps, the design focuses on preventing clogging. That's why you'll often see smooth channels and impellers with large openings. These features help debris pass through more easily, reducing downtime. Also, impellers can be open or closed. but in lift station wet wells, submersible pumps usually use open impellers. This design choice further helps prevent clogging and ensures reliable operation. So, understanding these principles allows us to optimize pump performance for different applications, balancing pressure and flow as needed while ensuring durability and ease of maintenance. Let's take a closer look at some of the different types of centrifugal pumps. First up, we have vertical wet well pumps. These pumps feature a vertical shaft and a diffuser design, with the pumping element suspended from the discharge piping. The column length can vary depending on the installation depth, making them quite versatile for different setups. Next, we have horizontal non-clog pumps. These are designed with an open impeller, which is a key feature because it allows them to handle solids-laden wastewater without clogging issues. This makes them especially useful in applications where solids are a concern. Finally, there are submersible pumps. These are fully submerged units with sealed motors, which means they can operate underwater without issues. They're commonly used in wet well applications, where the pump needs to be placed directly in the fluid. Understanding these varieties helps us select the right pump for each specific application, ensuring efficiency and reliability across different wastewater handling scenarios. Let's take a closer look at propeller pumps and the two basic types. First, there's the axial flow propeller pump. In this type, the flow of water is parallel to the axis of the impeller, meaning water moves straight through in line with the shaft. This design is particularly effective for moving large volumes of water at relatively low pressures. Next, we have the mixed flow propeller pump. This one combines characteristics of both axial and radial flow patterns. In other words, the flow is both axial and radial to the impeller. This makes mixed-flow pumps versatile for specific applications where you need a balance of flow rate and pressure. Understanding these two types helps us select the right pump for different situations, which is essential in optimizing system performance and efficiency. Vertical turbine centrifugal pumps are quite fascinating because they consist of multiple impellers stacked on a vertical shaft. Essentially, water enters at the bottom and is pushed upward through these impellers, which creates an axial flow, meaning the water moves straight up through the column pipe. One of the key advantages of staging the impellers like this is that it allows us to generate very high discharge pressures. As water moves through each impeller, the pressure increases, making these pumps highly efficient for high-pressure applications. You'll find these pumps used in situations where water needs to be lifted from deep wells, sometimes several hundred feet deep, or in cases where they're directly connected to the discharge head for shallower sumps. Their versatility is a big part of what makes them so valuable in various water management and industrial processes. Overall, they're an excellent example of how combining multiple stages and thoughtful design can achieve both high pressure and efficiency in fluid handling. Now, let's take a look at some of the positive displacement pump types. First up, we have reciprocating or piston pumps. These pumps work by having a piston move back and forth, which opens and closes check valves to move fluid through the system. One key point to remember is that you should never operate these pumps against a closed discharge valve, as doing so can cause damage from excessive pressure. Next, we have inclined screw pumps. These operate with a screw that turns at a steady speed within a trough, effectively moving wastewater up towards the discharge point. They are supported by bearings at both the top and bottom, which helps keep the screw aligned and functioning smoothly. Finally, there are progressive cavity pumps. These feature a screw-shaped rotor enclosed within a stator. As the rotor turns, cavities between the rotor threads move the material from the inlet to the discharge. An important safety note here is to never run these pumps dry or against a closed valve, as that can cause damage to the pump's internal parts. Connecting all these points to our overall theme, it's clear that understanding the different types of positive displacement pumps helps us select the right pump for specific applications, ensuring efficiency and longevity. Let's take a closer look at how a progressive cavity pump operates. The key component here is the screw-shaped rotor, which makes contact along the walls of the stator, usually made of synthetic rubber. When wastewater enters through the inlet valve, it fills these cavities created by the rotor and stator. As the rotor turns, it moves the material along the length of the pump toward the discharge end. One of the most important aspects to understand is that the size of these cavities directly determines the pump's capacity. That is, how much fluid it can move over a given period. These pumps are especially recommended for handling materials with higher concentrations of suspended solids, like sludge. They are quite effective because the design allows them to handle semi-solid or viscous materials without clogging or losing efficiency. Overall, this operation principle makes progressive cavity pumps ideal for wastewater and sludge applications, ensuring reliable and steady pumping even with challenging materials. Let's take a closer look at some of the critical components of a pump. First up is the shaft and sleeve. It's essential that the shaft is straight and true because any misalignment can cause vibrations, which over time can lead to wear and failure. The sleeve acts as a protective barrier, shielding the shaft from damage that might occur if other pump parts start to wear or fail. Next, we have the impeller. This is really the heart of the pump. It's attached directly to the shaft and is responsible for moving the water through the pump by creating centrifugal force. Without a properly functioning impeller, the entire pumping process would be compromised. Then we have the bearings. These are crucial because they support the rotating assembly. Radial bearings prevent any side-to-side wobbling, ensuring smooth rotation, while thrust bearings handle axial forces, keeping everything aligned along the shaft's axis. Proper bearing support is vital for the longevity and efficiency of the pump. Finally, there's the volute. This is part of the pump casing that collects the water as it leaves the impeller and directs it out of the pump. Its design helps convert the energy from the impeller into a steady flow, making the entire pumping process more efficient. Together, these components work seamlessly to ensure the pump operates smoothly and reliably, which is the core theme of our discussion today. Now, let's take a closer look at the different bearing types and their functions. First, we have radial bearings. These are designed to prevent side-to-side wobbling or radial movement of the shaft as it spins. They are crucial for maintaining stability during operation. The most common type you'll encounter is the standard ball-type roller bearing, which offers reliable support for radial loads. Next, we have thrust bearings. These bearings are responsible for supporting the shaft against axial forces, which means forces that act along the axis of the shaft. For example, they counteract the up-thrust caused by water entering the suction eye, as well as the down-thrust resulting from internal pressure. The typical choice for thrust bearings are angular contact ball bearings because they can handle these axial loads effectively. Understanding these bearing types and their specific functions is key to ensuring the system operates smoothly and efficiently. Proper bearing selection directly impacts the longevity and performance of the equipment, which ties back to our overall theme of maintaining optimal operation. Let's talk about suction piping installation. First, it's important to remember that suction piping is always larger than discharge piping. This helps bring water into the pump at about 4 feet per second, which is crucial to minimize friction loss and ensure smooth operation. In contrast, the discharge piping is designed to carry water away at a faster rate, around 7 feet per second. Next, when installing piping, always ensure that the horizontal runs slope upward toward the pump. This simple slope prevents air pockets from forming, which could otherwise disrupt the pump's performance. Another key point is the use of eccentric reducers. These should be installed flat on top, known as eccentric reducers, instead of tapered on both sides, which are concentric. This prevents creating air pockets and helps maintain a smooth flow of water into the pump. It's also vital to make sure there are no air leaks in the suction piping. Any leaks can draw air into the system, which can cause cavitation and damage the pump, so tight, secure connections are essential. Finally, support your piping properly. Never rely on the pump to hold the piping up. Unsupported piping can stress the pump casing or damage the rotating parts, leading to costly repairs. Proper support ensures the longevity and reliable operation of your system. Now, let's talk about preventing internal recirculation, and one effective solution is the wearing ring. When a pump is operating, water tends to try to pass from the high-pressure discharge side back to the suction side. This movement causes recirculation through the impeller, which can lead to inefficiency and potential damage. One way to address this is by machining the pump casing to close the gap that allows this flow. But as you might guess, over time, this fit can wear down and become less effective. That's where wearing rings come into play. These rings are installed between the pump and the impeller, and they serve to reduce the clearance, sometimes down to as little as 0.01 inches. What makes wearing rings particularly advantageous is that they are removable and replaceable when they wear out, unlike the casing itself. So, in essence, wearing rings act as a maintenance-friendly barrier to minimize recirculation, helping to maintain pump efficiency and extend the equipment's lifespan. This solution ties into our overall theme of optimizing pump performance through thoughtful design and maintenance strategies. Now, let's take a closer look at the stuffing box and packing. The stuffing box is the part of the pump where the shaft enters the casing. It's crucial because it needs to keep water inside the pump while preventing air from escaping. To do this, we use rings of pump packing that are placed inside the stuffing box. On top of these rings, there's a metal packing gland that allows us to adjust and tighten the packing as needed. Since these packing rings touch the rotating shaft sleeve, friction is inevitable. This friction generates heat, which can be problematic if not properly managed. That's why water needs to leak through the packing to cool it down. Typically, this cooling water comes from the low-pressure side of the pump. However, if the pressure isn't enough, we can pipe high-pressure water from the discharge side into the packing as seal water. It's very important to emphasize that without adequate seal water cooling, the packing can overheat. Overheating causes the packing to become glazed, which can cut into the shaft sleeve. This not only leads to packing failure, but can also cause severe damage to the shaft itself. So, maintaining proper seal water flow and cooling is essential for the longevity and safe operation of the pump. Let's talk about the lantern ring and seal water system. Seal water enters the stuffing box from outside, but it needs to reach the inside area between the packing and the shaft, where heat is generated. To do this effectively, we use a lantern ring, which is basically a metal ring with holes in it. This ring allows water to circulate around the outside of the packing and then pass through to the inside. It's a crucial component because it helps keep the packing cool and properly lubricated. Now, it's important that the lantern ring aligns correctly with the seal water port on the stuffing box. If you're using a potable supply for pumps that handle non-potable water, you need to be extra careful. In such cases, installing an air gap or a reduced pressure backflow preventer is essential to prevent cross-connections. These measures protect the water supplies and ensure the system operates safely and efficiently. Understanding this system is key to maintaining reliable sealing and preventing leaks or contamination, which ties back to our overall focus on safe and efficient pump operation. Now, let's take a closer look at mechanical seals, which are a key part of advanced sealing technology. Pumps that don't use packing rely on these seals, which consist of two highly polished seal faces. One face is mounted in a gland ring, replacing the traditional packing gland, while the other is attached to the rotating shaft with a locking collar and spring. This setup ensures that the faces are pressed together with a constant amount of pressure. When the pump is running, seal water plays a crucial role by forcing these faces apart under pressure. It's important to understand that during operation, the faces don't actually touch each other. Instead, friction from the water film prevents leakage from the gland plate. However, it's vital to recognize that if the seal water system fails, it can have disastrous consequences. Without proper seal water, the faces can come into direct contact and rub against each other. This generates destructive friction very quickly, which can destroy the seal in just seconds. So, maintaining the seal water system is essential for ensuring the longevity and reliability of mechanical seals. And by extension, the overall integrity of the pump system. Alignment is absolutely critical for the longevity of your equipment. Couplings are the parts that transmit torque from the motor to the pump, and getting them properly aligned is essential. When alignment is off, it can cause serious damage to the equipment and drastically reduce the lifespan of both the pump and the motor. Misalignment leads to excessive bearing loading, which puts stress on the bearings themselves. It can also cause the shafts to bend, leading to premature bearing failure. You might notice increased vibration during operation, and in some cases, it can even cause permanent damage to the shaft. There are two main types of misalignment to understand. First, parallel misalignment, where the center lines of the pump and motor shafts are offset but remain parallel. Imagine two lines that are parallel but not perfectly aligned. They're shifted sideways. The second type is angular misalignment, where the shafts are not parallel at all, but instead form an angle with each other. Think of it as the shafts leaning toward or away from each other. In reality, most misalignment involves a combination of both types. That's why our goal is to minimize both angular and parallel misalignment as much as possible. Using tools like a dial indicator can help us measure and correct these issues, ensuring everything runs smoothly and lasts longer. So, proper alignment isn't just a maintenance step. It's a key factor in protecting your equipment and keeping your operations running reliably. Understanding pump characteristic curves is essential for optimizing pump performance. Every pump operates most efficiently within specific conditions that are illustrated by these curves. On this slide, we see three key curves that help us interpret pump behavior. First, the head capacity curve, labeled as A, shows us the relationship between head pressure and flow rate. Essentially, it tells us how much pressure the pump can generate at different flow levels. Next, the brake horsepower curve, labeled as B, indicates the power requirement at various operating points. This helps us understand how much energy the pump needs to deliver certain flows and heads. Finally, the efficiency curve, labeled as C, shows us how efficient the pump is across its operating range. The goal is to operate the pump where it performs most efficiently, saving energy and reducing costs. For example, at 200 feet of head, this specific pump outputs about 350 gallons per minute, requires roughly 22 brake horsepower, and runs at around 80% efficiency. By understanding these curves, we can select and operate pumps more effectively, ensuring reliable performance and energy savings. This is a crucial part of pump system management and aligns with our overall goal of optimizing hydraulic systems. Now, let's look at some common operational problems that can occur with pumps and how they impact performance. First up is cavitation. You might hear sounds like marbles or rocks being pumped through the system. This happens when the pump discharges water faster than it can enter, creating a partial vacuum in the impeller. The main causes include a loss of discharge pressure, suction obstructions, or low suction head. Cavitation is serious because it can damage the impeller, so immediate action is required, usually by temporarily throttling the discharge valve to reduce the load. Next, we have air locking. This occurs when air or dissolved gases get trapped in the pump's volute, creating an artificial head pressure. Until the shutoff head is reached, the pump can't move water effectively, and it can overheat within minutes. Common causes are leaks in the suction line or failed low-level cutoff switches. To prevent this, installing air relief valves and repairing leaking gaskets are effective solutions. Finally, there's loss of prime, which happens when water drains from the volute and impeller. Without water, the impeller can't generate suction because it needs to be filled with fluid to work properly. This problem only occurs with negative suction head. Causes include worn packing or a defective foot valve. To prevent loss of prime, designing the system to maintain positive suction head is essential. Understanding these issues helps us keep our pump systems running smoothly and efficiently.